take a look at a couple of those and also kind of walk our way into what we'll be looking at today. So one of the things that I didn't cover was alkene nomenclature, which was on the homework. There was a problem similar to this one. This might have actually been the problem. If we look at naming this one, we're going to find 6 as our longest cyclic, our longest chain. So that's going to be cyclohex. And now we have a double bond in it, so that gives it the suffix -ene. So the parent name has the functional group in it. Now that functional group now tells us that that becomes a priority. Okay, for a alkene, that means that we want the lowest possible number for an alkene. And in a ring, we want the alkene to be 1 and 2. Okay. If it had been in a straight chain, right, we would just want the lowest possible number starting at one side. So that would have been 1, 2. The next one would have had to been 3, right? So it needed to be consecutive. If we went the other direction, it would have been 1, 2, 3, 4, 5. The 2, 3 beats the 4, 5. So we mark that one out, and it is 2, right? And since it's not a cyclic, we know that it had to start at one side and go the other, so we can just say 2. In the case of the cyclohexene, we got to make sure it's 1, 2. Why am I saying it has to be 1, 2? Because potentially you could say, all right, here's 1, and then that's 2. So I get the lowest possible numbers. But in this case, then this would be 6, right? And so this is not appropriate, okay? So we go 1, 2, which then means that my methyl is 3, 4, 5, 6. So I have 1 cyclohexene, 3, 6 dimethyl. Okay. Now, the 1 there can be left off. Why would the 1 be possible to be left off? What's the system? If I have a cyclic, where does the double bond have to be? 1. Right? So by definition, the cyclohexene has to be 1. So this could be 3, 6 dimethyl cyclohexene. The 1 doesn't add anything, so therefore it does not have to be included in the name. The other thing I wanted to review real quick was what we did Thursday. It's such a long time ago. And what I wanted to look at is looking at hybridizations. Before we get into resonance. So, you know, if we look at that carbon right there, that carbon has 2 hydrogens that aren't shown. And what's the hybridization of that carbon? So how many direct bonds does it have to another atom or a lone pair? 4. So since it has 4, that's sp3. So this is an sp3. What does sp3 tell us about that carbon? Well, it tells us that carbon is tetrahedral. Right? That the angles here are going to be about 109.5 or exactly 109.5, depending on how symmetric that is. It's going to tell me that all of the bonds are sigma bonds. So it gives me something about the geometry, it gives me something about the shape, and it gives me something about the overall bonding within that. So this identifying hybridization is pretty straightforward, but it also provides lots of information. If we look at this carbon, that carbon now has how many atoms directly attached to our lone pairs? 3, right? So that's sp2. And again, what does an sp2 tell me? Well, it tells me that I have a trigonal planar shape, right? That's going to be 120 degrees. It also says that I have a P left over, and that P goes to make a pi bond. So in this case, I have sigma and pi bonds. Yes, ma'am.
What would we look up to understand how you know that's stuff on those? Like how you said, like that's 4 bonds, that's sp3. Like what would we look up online to get help on that?
Hybridization, carbon hybridization. Yeah. What you need for every sigma bond, and that includes lone pairs, right? So every time I need a place for 2 electrons, I need a sigma bond, right? So what I need to do is take my S and my 3 Ps, and I need 4 or 3 or 2, right? And so of that, then if I need 4, that's going to be 1 S and 3 P, so that's sp3. But then sp3, whether it's nitrogen, oxygen, carbon, is always going to be tetrahedral, right? So it's going to be about 109.5. Now that's the geometry, not the shape. The shape could be tetrahedral, or it could be trigonal pyramidal, or it could be bent, depending on which atom that is, right? So really it comes down to needing to hybridize all of my carbons, right? So the hybridization just comes out of, and the hard part about this, and this is where it seems simplistic to just say how many bonds do you need, but it's not far from that, right? Because if I need 3 bonds, I take 3 bonds, and the last one remains as a P. Right? So in that case, I've got 3. I need to take these electrons, spread them out this way. Now, if this molecule then reacted, so if I went from this, and I will get to all the reactions later, so you don't have to memorize this one yet. So if I went from here to here, let's draw in our hydrogen. So there's 1 hydrogen, 1 hydrogen, hydrogen. What I've done is added 2 hydrogens right across that double bond. What's happened is that I've gone from an sp2 carbon to what? I need an sp3. So the reaction was not only that I added hydrogen across there, but I had to rehybridize my electrons, my orbitals, right? So that I can now have 4 sigma bonds. So I started with 3 sigma bonds, sp2, and then in that reaction, I went to 4 sigma bonds. That meant that carbon had to rehybridize. So the reaction was the addition of the hydrogen across that double bond, turning that p orbital, which was part of that pi bond, into a new rehybridized carbon, which sp3. So the hard part about this when you're thinking about this is, why is it sp3 now? Well, how many bonds does it need? It needs 4 bonds. So if it needs 4 sigma bonds, right, either sigma bonds or lone pair spaces, what's this hybridization going to be? Well, sp3. Yes, ma'am. So over here, the P is if you look up here, right, the P does have an electron in it. But what that P is doing is not making a sigma bond, right? It's making the pi bond. So our sigma bonds are all the direct overlaps. And our P bond So our p orbitals are making the pi bond. So what happens is this converts to that. Okay. So I rehybridized, I took that P back in to the SPs, the sp2s, right? I rehybridized it now that I could have a sigma bond with my hydrogens. Yes. Well, what you need is a catalyst. So either a hell of a lot of energy or a catalyst. Okay, questions about this one? All right. If we looked at the bottom one here, again, kind of thinking about what does this tell us? That carbon right there only has 2 sigma bonds, right? It has 4 bonds, but 2 sigma bonds, 2 pi bonds. So 2 sigma bonds, that's sp. So that's sp. It tells me that it is linear, right? And a linear is 180 degrees. Okay. It tells me that it has 2 sigma bonds, right? And 2 pi bonds. Okay. Other questions about this? So let's go ahead and look at resonance. So if we look at the resonance, first we need to think about what's going on here, okay? And we have a bunch of sigmas, but we also have a pi bond, right? And that's a p-p overlap. Remember when we talked about the hydrogen and that whenever it combined, we always get a lower energy bonding state and we get a higher energy anti-bonding state? Whenever you get to pi systems, you would have some sigmas. You'd have some sigmas down here and you'd have some anti-sigmas up here. But the 2 energy states that are going to be the closest, they're going to be these pi's, right? So if you think about it, the sigmas are much more stable, they're stronger. They're going to be down here. The anti-sigmas are going to be much more weak, right? Because if you get to an anti-bonding sigma, you've actually broken a sigma bond. And then we've got, in the middle, we're always going to have our pi bonds. So you kind of go from your sigmas up to your pi's, then to your anti-bonding pi's on up, right? And this little asterisk here is the anti-bonding. So this is my anti-bonding. This is my bonding. And for this one, right, we put our 2 electrons for our pi bond into the bonding. That would demonstrate what we've shown here with this molecule, right? This would demonstrate that we've got a bonding pi orbital. Now, if we took and added a bunch of energy, you know, and for this one, we can use UV energy. We could take and move one of those electrons from the bottom to the top. The result of that is that my pi bond now is no longer stable, and it's not really bonding, right? So we've moved an electron up, it's no longer bonding, so it's non-bonding. What we get is these radicals. What's happening here is a similar thing that happens whenever you add UV light to almost anything, right? So if you add UV light to your skin, so you're out in the sun, you're sun tanning, one of the things that happens is your body starts to absorb that, and your bonds can go from bonding to anti-bonding, particularly your double bonds. And what those can do is these are then radicals. Okay. And radical is just a lone electron like that. And radicals are high energy and they like to combine. So one of the reasons that skin gets tight whenever you suntan too much, or if you smoke does a similar thing. You get a lot of wrinkles. That's because the skin molecules are forming these little radicals, and then the radicals are combining across the skin. So it becomes leathery because the skin is not as flexible, because you now have covalent bonds between these parts of your body, right? So you can do the same thing with smoking. You can do the same thing with getting a lot of sun, right? It gives that leathery feel to it, because this is what's happening, right? Now, when we think about that, then we think about, okay, well, how do we keep that from happening, and what's going on with different things? Well, what we can do is look at something with more double bonds. So here we have 1,3-butadiene. Now, in this case, right, how many p orbitals do we have? Well, this is sp2, right? So if we leave our sigmas alone, we've got a p orbital here, p orbital there, p orbital there, p orbital there. And what this is suggesting is that these are overlapping and that's overlapping. But we can also show this as this. And what we're going to look at, so we've got these four. So what I'm doing is just straightening it out to make it a little easier to draw, right? And we can think about those electrons as being in phase or out of phase. What's demonstrated over here is that these two are in phase and those two are in phase, and I have a node between the two. Remember, a node is a place where we have no electron transmission, right? So what this is suggesting is that these two on this side, okay, are not communicating with these two on that side. But since there's 4 pi p orbitals, how many pi orbitals should I have? If we look up here, we had 2 p orbitals. And how many pi orbitals did I have? I had the pi bonding and I had the pi anti-bonding. So I had 2. So here, if I have 4 p orbitals, how many pi orbitals should I have? I should have 4. I should have 2 that are bonding, right? Half, and the other 2 should be anti-bonding. So let's look at all of those and show what that looks like. So what I'm going to do is show my p orbitals, and I'm going to do it energy here. And I'm going to start by just showing and as we increase in energy, what we want to do is increase in nodes. So make it a little easier to demonstrate that. I'm going to turn it into a string here with 4 dots on it. And now if we look at the first one, right, what would be the lowest possible energy? Should we have, so let's think about our atomic orbitals. Atomic orbitals, we start with S and we go to P and then D. A P has how many nodes? It has 1 node, right? Because we have the over and under, right? Right here in the middle is a node. But what comes before the P orbital? The S orbital. How many nodes are in the S orbital? 0, right? There's all the electrons are communicating in an S orbital. They're in this view of what is a sphere, right? But whenever we go up, when we go to a D, we have 2 nodes. When we go to the F, we have 3 nodes. Same thing, same principle is really kind of playing here. So in the first one, really we have no nodes, right? So we'll draw a string like this, and this is the chemistry string theory just to show this is not the physics string theory. So this was shown to help people understand molecular orbitals. So the string goes across, then the string's going to go through the middle, 1 node, right? We're going to cross that line, and then we're going to go 2 nodes, and then we'll go 3 nodes, 3 crossing those lines. The impact of that is if we look over here with our P's, so if we look at our P's over here, if all of those, there's no nodes, what does that mean as far as the phasing of our p orbitals? Well, all of them are in the same side, so we can color one side of those all the same. If we look at our second one, we have 1 node, so that means we have, oops, that is incorrect. Fix that. And then here we have node up, and then 2 nodes down, and a node up. And then on the last one, we have a node down, up, down, up, down. Now, if we look at these, right, I have 4 of them. So what are these bottom 2? Well, they're my pi bonds, right? And then my next ones would be what? My pi star. So the top 2 are my anti-bonding. My bottom 2 are my bonding. Now, if we wanted to show these, what's happening in this bottom one? Well, it kind of suggests that everything is in communication. And then the second one here, looks like this one, which is what we show our molecule as. And then our next one is actually something like this, right? So we're starting to get some things that aren't bonded together. We get some radical p orbitals that are isolated. And then the last one, right, we could assume that all of those electrons aren't communicating. There's a node between them, so they're not communicating, so there's no real bonds. Okay, I wrote two words out here, HOMO and LUMO. HOMO is highest occupied molecular orbital. And that comes from the fact that if we look at our electrons here, how many electrons do we have in 4p orbitals? Well, we have one electron for each p orbital, so we have 4. So those would be our pi bonds, pi electrons, right? So our highest occupied molecular orbital is this one. This would be not the highest occupied molecular orbital. And then LUMO stands for lowest unoccupied. If we were going to take one electron and excite it, where would that electron go? It would go from our HOMO right here to our LUMO. We'll get to this later on this year, but for right now, it's important just to go ahead and introduce this because we're not going to come back to this for a while, right? So this is kind of foreshadowing. The HOMO to the LUMO. This is the reactivity that's going to be the most important. But what does this also suggest about the molecule? Is there no communication right here? Are this double bond and that double bond totally acting as if they were totally isolated? No, because of this, right? That is an orbital, that is filled, right? So therefore, this is part of that overall structure. The LUMOs, the unoccupied, right? They're not. They're there, they exist. If I need to do the reaction, they are there if I excite the electrons into them. But the occupied ones do exist, which means that there is communication right here. This is the essence of resonance. So when we talk about resonance, what we're really talking about is we've got a line structure formation of a couple of pictures that shows us the overall picture, right? If we wanted to show the overall picture here, you know, we'd have to show that this and this coexist. The way we can usually tell that is that this rotation energy is higher than we would expect. Why? Because that double bond over here is communicating with that double bond over there. And the only way they can communicate is if they're lined up, right? The p orbitals have to be in alignment. As soon as the p orbital goes to orthogonal, 90 degrees, right? Then there's no communication. Why? In a p orbital, what's in the middle? A node, right? So they have to be lined up. So therefore, when we're looking at these structures, it wants to be lined up like this. If it goes like this, there's no communication. So therefore, rotating around that single bond between those two double bonds is higher than if I just went and rotated that bond. Oh, that's a sigma. So now we're going to start looking at some examples of resonance. But realize what's going on with resonance is that we have a molecular orbital definition of that. What do you notice about all the p orbitals here? Did I ever change my sigma bonds? No. So my direct connectivity did not change. So in resonance, you do not change the connectivity, the sigma bonds, but you can change the p orbitals, right? The pi bonds and the lone pairs, because that's not changing the connectivity. A good example of this is just carboxylic acid. In a carboxylic acid, I can show my electrons, moving. So I moved a lone pair up towards the oxygen, and I'm going to change some colors here so that makes that purple, like this pink. Where students usually get confused with resonance is you think it's just a flip of a molecule in space, right? So if you look at these two, if I didn't put one oxygen as pink and one oxygen as purple, you could think that I just rotated it through space. That's not what's happening. What's happening is I'm moving electrons. Now, what the reality of this molecule is that hybrid model, right? What I'm showing here is the two potential homos at the top, right? But what that is the reality is this. In many textbooks, you'll see the example of, you know, a unicorn and a dragon, and the reality is that it's a, you know, rhino, right? What happens is because we have this combination here of all of our bonding orbitals, is that what we usually show for the molecule is just one of the possible representations. When we look at our resonance structures here, the reason that you should need to learn these, and you'll have several problems over resonance, is that these are both equivalent representations of that molecule in our limited concepts, right? So we're having to draw this on a piece of paper. We're coming up with a limited concept. What if we could easily go in and do this on paper, and you'll see it in some of probably in the textbook, there's probably a big drawing on it, is that it looks like this, right? With an electron cloud. Instead of like this. Right? That electron density is actually spread out throughout those two oxygens. What does that mean as far as the stability of those oxygens? Which oxygen is more stable? Well, they're about the same, right? But if we compared that which of those two oxygens is the most stable? In the first one, I can draw a resonance structure so that I've spread out that electron cloud, the electron density to two atoms. In the second one, can I do that? No, this is sp3. There's two hydrogens here. There is no pi orbital. There's no way to move electrons without breaking a sigma bond, right? So therefore, resonance-wise, this breaks one of the fundamental rules in resonance. I can't do that. So this is isolated. So this is going to be less stable. So if I was going to take a hydrogen off of one of these, which one of these two would be easier to take the hydrogen off of? The first one, the alcohol, or the second one, the carboxylic acid? The second one, right? This is going to be much more stable than that, which means that this hydrogen, right, is more reactive because by pulling off that hydrogen, I'm creating a more stable, and this one is going to be less reactive. So the reason we identify, and that's what you'll be doing on the homework, identifying resonance is so that I can identify reactivities. And because we do not have the easy ability to type in a molecule or draw in a molecule and then hit a button and get the electron cloud, we also have to learn how to draw the resonance structure. So let's try that. I'm going to give you a couple examples. I want you to draw the resonance structures for them. So on the first one, let's look and see what we have going on here. So we have a p orbital here, right? Do we have a p orbital here with a positive charge? Well, the positive charge says that I have one hydrogen, right? So I have a hydrogen and then a positive charge. If we look at our hybridization, what is the hybridization here? Well, I haven't shown it, so let's go ahead and show it. Okay, so we have two hydrogens there, hydrogen there, right? I know that because it needs 4 bonds. So 4 bonds, but one of them is a pi bond, so I have 3 things attached, no lone pairs. So that's sp2. Here, 3 things attached, no lone pairs, sp2. Here, the question mark that with that carbocation, right? I have 3 things attached, so that's sp2. Here, sp3, I have 4 things attached. So what's happening here with this, that positive, is that I have electrons, right? There's no electrons here. It's positive. If we look at our electrons, what are we going to do with our electrons? Move our electrons towards a positive or away from a positive? Towards, right? Positive is a low electrons density, right? So we move from high to low. So we're going to move that there. If I move that there, what happens with my electrons? Well, now I've got a double bond there, and I got the positive there. So these two are the resonance structures. Don't be afraid to back up and draw this, okay? You're still learning how to do this. What you'll see sometimes in the textbook is it just jumps right to this. You'll even see it in the online homework. That's because they're assuming that you've gone from this to that. Okay. Don't be afraid to back up and do exactly what I did over here. And the more you do this, the faster it'll get you to this and answering those problems really quickly. Okay. So don't worry about backing up. When you see it in the book, it looks kind of magic. Back up, draw all of your hydrogens, draw all your hybridization. Okay, so let's do that same thing with our second one. So in the second one, I have hydrogen, hydrogen, right? Need four bonds there, right? Now this one has a negative charge, right? So that means I've got an extra electron, that's a lone pair, right? So that's a negative, and then on the last one, I have hydrogen, hydrogen. Right? So I've got one hydrogen, but now I've got an extra electron, not a lost electron. We look at our hybridizations, sp2, sp2, here, sp3. Then here, sp2. sp3, sp3. So that lone pair, that extra electron gives me a lone pair. That means I have 3 things to bond to, and a lone pair. I need a space for 4 paired electrons, right? So therefore I get sp3. Yes, ma'am. Here, there's only three atoms attached. So there's hydrogen, hydrogen. So carbon always has 4 bonds. It's not the bonds, because you can have sigma and pi bonds. It's how many atoms and lone pairs. So how many direct overlaps do you need? Right? And so here we've got 1, 2, 3, and then this is another, it needs space for those, right? Where here, this pi bond, right, is going to be outside, right, above and below the sigma bond. So I really only need 3 sigma bonds and then 1 pi bond. Okay. Here I need 4 sigma bonds. So all carbons have 4 bonds unless they're positive or negative charged. So in this case, let's draw it again. I don't have an sp2. What I have is this lone pair, right? But the nice thing about lone pairs is they're electrons that aren't attached to anything. So therefore, they can move around too, right? So they can move. So I can draw these structures here going there, right? And we go from high density to low density. So we're going to go from the negative, right? And then we transform that. Now let's show a possible example of where this will become important. Again, foreshadowing. So if we take a bromine and react it, we get two products? Why do we get two products? Because that's in resonance with this. So therefore, if the negative bromine reacts with the first one, I get the first product, right? So if that reacts with that positive, I get this. But if this reacts with the resonance structure, I get, oops, I get that. Questions about this one? Yes. Yes, in most cases, right? Now, in this case, it depends on what the conditions were for this, and we'll get to this later. But the conditions could be what we call thermodynamic or entropy, right? So if it's thermodynamic conditions, then you're going to take which one is more stable, right? And so for that, we need to know something about the carbocations. Which of these two carbocations is more stable? This one or that one? Well, in a carbocation, is it electron rich or electron poor? Electron poor, right? It's got a positive. It's got less of electrons. So therefore, it wants to be stabilized by what? Electrons. So in this case, this carbocation has 1, 2 carbons and a hydrogen attached. Which atoms have more electrons? Carbons or hydrogens? Carbons, right? So the carbons, through something we'll discuss later, can contribute electron density, not full resonance, right? Just electron density to this positive charge. Over here, how many carbons can give electron density to that positive? Just the one, right? So if we're looking at thermodynamic, which of these two products is more likely? This one, because that's more stable. So although these are in resonance, they're not always going to be 50-50%, right? So if I was looking at entropy, it would just be fast. Which one reacts the fastest? In that case, this one has a little bit of an advantage because there are only two hydrogens. There's two hydrogens, right? And not the other carbon. So if that bromine's coming in, it can come in faster because there's nothing blocking it. But if we're looking at thermodynamics, the overall stability, this one has the advantage. So depending on the conditions, I would either get a majority of this or potentially a majority of that. Okay. At this point, we'll get to that point, right? So right now, you just need to be able to draw your resonance structures. I just wanted to show you how we're going to use the resonance structures. So we're building up, drawing resonance structures right now, and then we're going to move to using those resonance structures. Okay, questions about resonance? Okay, let's try a couple harder ones. Okay, so let's take a minute or so, draw some resonance structures for these two. Okay, let's look at the first one. Okay, what I like to do with these is I like to follow my electrons. So the first thing I'm going to do is I'm going to move these electrons there. If I move this set of electrons there, that's going to mean these electrons have to go here. Now the check on these is to see if anything had to break. Did I have to break either, oops, there's only one. Did I have to break this hydrogen bond here? No, by moving this in and that out, right, it still has 4 bonds. I didn't have to break anything. Here, there's only one hydrogen. By moving that out, it moves the pi electrons there, but it doesn't break anything. So therefore, I can show that now this oxygen is double bonded. I've got a negative charge here. Again, these are resonance, so they can go back and forth. I can do this again, move this electrons here, these out. Oops, dropped my oxygen. And so I have 2 sets of electrons here, two resonance structures, or 3 resonance structures, right? And we can say that all of these are in conjugation, right? So they're all in conjugation. Conjugation means that they're all communicating with each other. In the bottom one, we can move these electrons there. Give me a positive charge there. Can we move the positive over to here? Sorry, you can't see that. Can we move the positive to this double bond? Well, if we draw in our electrons, our hydrogens, right? We have 4 sigma bonds here, so this is sp3. If it's sp3, then what does it have? No pi bonds, right? Pi electrons. What would have to happen if I tried to take electrons and move through that sp3 carbon? I'd have to break a bond, right? I'd have to break a bond with the hydrogen. That's changing the connectivity. So therefore, when we look at this structure, this is in conjugation. It's a continuous pi system. This one is isolated. Okay, so just because something has pi bonds, double bonds, or triple bonds, doesn't mean necessarily that they are communicating with each other. If they're isolated, they behave as if they're isolated, right? If I added something to this molecule, those 2 double bonds would act like single double bonds. There just happens to be 2 of them in the molecule. But if you're in there in conjugation, that changes the reactivity and the way they behave. They are in communication. So think about conjugation as communication, right? And non-conjugation or isolation as not communicating. And they communicate if there is a pi system they can work with. Because it's in your textbook right now, I'll go ahead and touch on this. We'll get to it a little bit later, and that is aromaticity. Sorry, the drawing gets confusing really quick. What happens in aromaticity is that I have a continuous continuous cyclic pi system. So if we wanted to draw, you know, the resonance contributors, we could rotate those double bonds. But in reality, this is going to behave as if it was a continuous system. Because of this, aromaticity creates very stable pi systems. And we'll get more to aromaticity when we get to reactions, but it is brought up in your textbook here, so I wanted to at least touch on it. So it's got a continuous pi system, right? So that gives us this system. Biologically, since this is biological emphasis, it turns out that this pi system above and below that ring becomes a secondary attractive force. There actually can be electrons density transmitted above and below aromatic systems. So one of the questions for a long time was, why are there so many aromatic systems in, let's say, DNA and RNA and so forth? Well, it turns out that there's actual communication not only in the fact that those are always flat, right? Those are these big, and that's what the first thought was, they're these big flat things. That's how you get a structurally flat thing, is you make something aromatic. But it actually turns out that there can be communication between two aromatic rings through space. Okay? And that through space communication can actually be an intermolecular force in of itself. It can also transmit electron density through that ring system. Okay, so I'm foreshadowing a lot today, sorry, but when you see aromatics in biological systems, realize that there's probably more there than just the fact that it's one big flat ring. Okay. So that brings us to intermolecular forces. And let's talk about the simple ones first. So ionic intermolecular forces and ionic intramolecular forces are really the same thing, right? So if I have a bunch of salt in a cube, right, I'm going to have interactions not only this way, right, but I'm also going to have it that way, right? In organic molecules, what we're going to see is okay, we could have something like this. Get a positive like that. So ionic forces are very strong, right? They're positive and a negative attracted to each other. They're an electrostatic attraction. And because of that, because of this strong positive and negative attraction, they have a high energy, right? They'll stick together very strong. And so salt molecules, anything with positive, but also in organic molecules, anytime you see a negative or a positive, right? That's going to be an obvious sign that you have ionic. The next one down is hydrogen bonding. When you get to hydrogen bonding, it's not a form of intramolecular. So ionic is both intramolecular and intermolecular. But in hydrogen bonding, what we have going on here is we have an attraction between the lone pairs of a heteroatom, such as oxygen or nitrogen, and a hydrogen atom. It has to be something that will hydrogen bond, and there aren't that many things that will hydrogen bond. The ones you'll see are oxygen, nitrogen. Fluorine does hydrogen bond, but it's odd because the only thing that fluorine only has one bond, so therefore it's only one molecule, hydrogen fluoride. But the rest of these can be alcohols, amines can hydrogen bond, thiols can hydrogen bond. Hydrogen bonding is very important in biological systems, right? In fact, the way that DNA works is by hydrogen bonding. In one base pair, there are two hydrogen bonds that will line up with each other. In the other base pair, there are three. If you think about it, it's almost a simple binary 1 and 0 system, right? Two hydrogen bonds, three hydrogen bonds. And that is what keeps DNA structured together in the helix, right? To break it apart and use it, so messenger transcriptase, right? What you do is you break open that and then you use that to replicate itself, right? Now, these aren't identical. That one is not identical to that one. They match, right? So if you think about it, it's something like that, right? So, but that's all that's really there. That is the difference. You can tell if you're going to have a place where it opens up. Does anybody remember what type of sequence you would have when you get a place where you'd expect a DNA or an RNA to open up? Okay, when you have ATs, AT, AT, right? So if you have a lot of A's and T's, all of a sudden you'll get that. Well, that's the double bond, only two hydrogen bonds. Where if it's G and U, I get confused between those two, then it's going to be three. So you get two hydrogen bonds, three hydrogen bonds, right? So hydrogen bonding is important, right? But it's not an actual covalent bond. You'll see that in some older biological books. It's not a covalent bond. It is just an intramolecular attraction, okay? It's easy to recognize. The last one is dipole. And for dipole, we need to, is a little bit more difficult to, it's not difficult to recognize, but it is important to understand what's going on. In dipoles, what you need is to know that there's going to be unequal sharing. So we have polar covalent and nonpolar covalent. Nonpolar covalent is an equal sharing. Polar covalent is a non-equal sharing. If we look at chlorine, chlorine is more electronegative than carbon. If you don't remember, we've got our periodic table. Fluorine, everything goes towards fluorine, right? Fluorine is the most electronegative atom. One way to kind of think about this is the closer they are to a noble gas, the more electronegative they're going to be. The more they're going to desire that electron density. The further away they're going to, less they're going to attract that electron density. Things in the middle, they like to share. So therefore, the chlorine is going to pull electron density towards itself. As it pulls electron density towards itself, right, then that means that the carbon is going to have less electron density than it might have had, and the chlorine is going to have more electron density than it might have had. if we look at, ethane, here we get an equal sharing, right? So there is no electron density difference between the carbons, so we get electron sharing. How about electron density between the carbon and the hydrogen? The hydrogen is not going to have much ability to keep its own electrons, right? But does the carbon need those electrons either? Is carbon something that really wants electron density? No, it's in the middle of the table, right? It likes to share. So there's a very, very, very minute electron density difference. So we usually call that nonpolar, right? There's a little bit there, but not a lot. Not enough for it actually to be a dipole moment. So if we have bromine up here, bromine is going to be electronegative, right? It's going to want that electron density, so therefore I have a charge, and this is a dipole moment. This is one way to show it, this little negative. What you're showing is, let me go through that again. The bromine is more electronegative than the carbon, so it's going to have electrons going towards it. And then I cross the bottom with that, saying that side's going to be positive, right? So when we show this, this is partially negative, that's partially positive. If we look at this example, we have carbon with 4 chlorines around it. Is there going to be a bond dipole towards the chlorine? Yes, that's going to have one. 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 Right? But if this is going that way, that's going this way, that's going that way, what is the dipole moment of the molecule? None, right? So therefore, we show that by doing mu 0, right? So they're all balanced. All of the electrons are being pulled away equally from the carbon in 109.5 degree angles, which overall gives that molecule no dipole. Okay. Those bonds are polar, okay, but the molecule does not have a dipole. Where this gets into intermolecular forces, and I need to know whether it has a dipole moment or not, is that when we see something like this, there is going to be an attraction between the partial negatives right, and the partial positives. So if we think about ionic, there's actually positives and negatives. That's going to be very tightly bound. Right? When we get to hydrogen bonding, now we have this hydrogen that's going to be really partially positive, and the oxygens or the nitrogens going to have a lone pair, right? That's going to be pretty tightly bound. And then dipole moment's a little weaker, right? Really, there's this charge difference, right? A little bit of a partial, more electron density on one side, a little less electron density on the other side, which sets up this partial positive, partial negative solution, right? So that's going to be dipole-dipole. Okay, so we start with ionic, go to hydrogen bonding, and then dipole. When we don't have a dipole, that's when we get into London dispersion or van der Waals. And this is an interesting history. Van der Waals, London dispersion, they both were really kind of discovered at the same time. but they were discovered during a war. So one group called it one thing and one group called it the other, and we still have both names. What these are, right, is if we look at what is attracting this molecule to this molecule in a liquid, right? If the molecules aren't attracted to each other, right, they would not want to be close. There's a little bit of attraction here. What these are doing is just, if we look at what's going on with our electrons, the question is, will the electrons in a molecular orbital spelling. Long question, right? Will the electrons in a molecular orbital be evenly distributed all the time? Will we always have a balanced electron density around a molecule? Remember, this not atoms, right? We're not talking about electrons being stuck to an atom. This is a molecular orbital. Those electrons can be moving around in that electron cloud. Is it always going to be balanced? And for van der Waals or London dispersion, no, right? It's not going to be balanced. At any one time, and the best example of this is, it's hard to show here, but it's easy to show between bromine and bromine, right? Bromine and bromine, they are equivalent, right? But at any one instance, I could end up with a positive and I could end up with a negative, right? It's just the instantaneous dipole. If we look at the electrons in a molecular orbital at any one time, there potentially could be an imbalance. That imbalance would end up giving us a partially positive and partially negative. That instantaneous dipole then causes attractions between molecules. Weak attractions, right? Because they're instantaneous, they disappear real quick, but they're still attractions. So if you have molecules, a good example of this is going to be diesel, right? Diesel is still liquid. You can still see a little bit of vapor coming off the top of diesel fuel, right? But it still is a liquid, right? There's attraction between those atoms, right? They bump into each other, but they don't bump into each other and they just go away. There's a little bit of attraction there. So as we're looking at these, okay, and we're running out of time. So this is another problem you're going to have to look at. You're going to have to recognize ionic, hydrogen bonding, dipole, and van der Waals. How do you recognize these? Well, you look at your molecule. If it has a positive or negative charge, it is ionic. If it has a hydrogen bonding hydrogen, then it can be hydrogen bonding. If it has a partial positive, partial negative, meaning if it has a strong electronegative atom and it has a non-strong electronegative atom, so a differential, you're going to get dipoles. And then the last one, if you more or less have a balanced molecule, right? All carbons and hydrogens are all two bromines, right? Two oxygens. That's going to be our weakest, right? Our van der Waals. So start with the easy to recognize and work your way down every time you get one of these questions. All right? Okay.